All right, so the hydrogen atom in the emission spectrum. The visible emission spectrum of the hydrogen is referred to as the Balmer series. So in this case here, this is where any electron starting above 2 will transition to the level 2. And this will be somewhere found in the visible spectrum or nearly visible in the ultraviolet. So this is a special series which is known as the Balmer series. So a transition down to 2. So if you look at my little picture here, a transition down to 2 could be at any one of these jumping all the way down. So let's go ahead and try some colors here. So I'm going to start here and jumping all the way down. This would potentially be seen as I do the next color. Once again, this is not specific colors. I'm just going to use it to kind of visualize that there is potentially different photons that are going to be emitted in this case here. And once again, these are just 4 potential photons that could be emitted. There would be, in fact, a lot more that transitions between 5 and 4, 5 and 3. Those will also be emitted, but once again, we're focusing on these ones, which are the Balmer series that always end in n equals 2. So using the energy in the diagram, the hydrogen, a wavelength of a photon emitted when the electron goes from 4 to 2. So looking at this, we are going from 4, which is 0.85, down to 3.39. So let's use that to find the first part. So question A, we are doing a change of energy of a photon, which is once again EF minus EI, final minus initial. The final energy is a negative 3.39. And we're subtracting it from the initial of a negative 0.85. So this energy difference, or this change of energy, is referring to, once again, the energy of the atom. So even though it's losing or has a negative 2.54, oops, that's not a 4, 2.54 electron volts, that means the photon would also have an equivalent of 2.54 electron volts. So therefore, the energy of the photon would also be a positive 2.54 electron volts. To solve for its wavelength, we're using that same equation, hc over energy. So 4.14 times 10 to the negative 15 times 3 times 10 to the 8, oops, times 10 to the 8 divided by 2.54, and we end up getting a wavelength of 489 nanometers. Okay, so this would definitely fall in the visible spectrum. How many different photons can be emitted by an electron transitioning from 5 to 2? So it's saying from 5 to 2. So I'm going to erase these for a second. So 5 to 2 is saying that, okay, so as it jumps down from 5 to 2, that's 1. But it could also do a 5 to 4. And then it could also do a 5 to 3. Actually, I'm going to try this again. I'm going to do smalls first. So we'll go 5 to 4, 1 jump, 5 to 3, 2 jumps, 5 to 2, 3 jumps. So those are 3 possible photons. But what about the photon that was ending at 4? Well, that one could then transition from 4 to 3, or it can go from 4 to 2. Well, once again, what about the transition between 3 to 2? There's also one at this point here. So in this case here, if you count out my arrows, we have 1, 2, 3, 4, 5, 6. And they're all slightly different lengths. Even though some of them look very similar, they will have different lengths here. So the question is, which ones of these are visible? So the answer is, well, how many there is? Well, there's 6 of them. So B, there is 6. How many are visible? Well, we need to remember, what does visible mean? So we're talking about roughly 400 nanometers to 700 nanometers. And I already know the one from 4 to 2 is visible. So 4 to 2, that was number 5 here. That one is visible. So let's try maybe the really small one, and let's try the really large one to kind of see where our balance is. Or what we can do is find out which ones would then fit in terms of energy levels, and which ones are roughly the difference, okay? So this one actually would take a few steps. So let's try this out. So first one, if I look at energy number 1, the transition jump 1, the change of energy of that is from final minus initial. And then we're just going to use that equation to figure that out. So negative 0.85 minus negative 0.54. Okay. Number 2, I'm pretty sure will fit, but let's try it out anyways. So the change of energy here for 2 is final minus initial, negative 1.51 minus 0.54, negative. Okay, so those are some small ones there. Number 3. So we're going from 3.39 and then 0.54 again. And I'm just putting them as positive values, as you can tell. So these are the negative. They all should be negatives. But I'm just saying, well, the photon would then have the positive of those. Number 4. And we just kind of continue through. So I'll let you guys work those through. But then what I would do is probably look at this and say, well, if E is equal to hc over lambda, well, if I can solve for the energy of 400, so 4.14 times 10 to the negative 15 times 3 times 10 to the 8 divided by 400 nanometers. I'm looking for something within the range of 3.105 electron volts to 700, which has an energy level of, let's try. A 1.77 electron volts. So in other words, I want to look for values within those. So if they have an energy level between this, we're going to say, yes, it's visible. If it's beyond that, we're going to say no. So right away, just from these first ones that we tried, I'll let you guys try the rest out. We're going to say not visible because it's lower than 1.77, not visible because it's lower than 1.77, and yes, visible because it falls within that range. Okay. And then it says the region of the spectrum when it goes from 2 to 1. 2 to 1 looks like a very large jump. So just quickly, number C, letter C. The transition between 2 to 1 is a change of energy, final minus initial, or negative 13.6 minus a negative 3.39. And I'm going to guess because it's going to be larger than 400 in terms of energy, larger than 3.01, it's going to be more energy. So we'll see what that looks like. Negative 13.6 minus negative 3.39, and I get negative 10 or 10.21 electron volts, which is greater than the visible spectrum. So I'm going to say that this is probably in the ultraviolet. Okay, just as a